Okay, question 4 asks us to create a polynomial function that has 4 zeros. One is the complex 0, 1 minus 2i, and one has the irrational 0, 1 plus square root of 3. And we are asked in this case to multiply the function out so that it's not left in factored form. Well, if 1 minus 2i is a 0, then that means we have a factor of 1 minus the quantity in parentheses 1 minus 2i. If there is a complex 0 at 1 minus 2i, there has to be 1 at its conjugate, 1 plus 2i. And that is also contained within parentheses. The same would be said for the irrational 0. 1 plus square root of 3 is inside parentheses, but there is a conjugate, there's a 0 at its conjugate, 1 minus square root of 3. And so there's the factored form just based on what we're told about the fact that there's 4 zeros and here's 2 of them. And then I rearranged the parentheses here in order to use the difference of squares identity. So I move the parentheses to wrap around x minus 1 and leave the 2i here, minus 2i and plus 2i. And same thing for the irrational. I wrap the parentheses around the x minus 1, so x minus 1 here and x minus 1 here. And we have a plus square root of 3 and a minus square root of 3. Well, when you multiply these two factors together here, you have the quantity x minus 1 squared minus this 2i squared. And the same thing happens for the irrational. When you square x minus 1, you get x squared minus 2x plus 1. Now, if that does not readily come to mind, just do that on a piece of scratch paper, pause this video and multiply that out, and you'll see that that is the perfect trinomial square that results from squaring x minus 1. Then we square 2i. Well, the square of 2 is 4, but the square of I is negative 1. So that makes quantity 2i squared negative 4. Well, then that makes this x squared minus 2x plus 1 minus a negative 4, which means plus 4. So this this part of our polynomial multiplied out then is x squared minus 2x plus 5. Over here, a similar thing happens, except there's no I to make this negative. We just square the square root of 3 and we get 3. So this is, again, x squared minus 2x plus 1, and we're subtracting this square, 3. And 1 minus 3 is negative 2. So there's our two trinomials, x squared minus 2x plus 5 and x squared minus 2x minus 2. Then we multiply these two together. Now, to multiply polynomials, you're used to the FOIL acronym for multiplying two binomials, but when there are more terms than 2, you just multiply each term in one polynomial by each term in the other. So x squared times x squared gives us x to the 4th. X squared times negative 2x gives us negative 2x cubed. X squared times negative 2 gives us negative 2x squared. So we've multiplied this x squared times everything in here. Now we move on to the negative 2x. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 2x is positive 4x squared. Then negative 2x times negative 2 is positive 4x. And that is, now we've multiplied this term in this trinomial times all of these terms. And now we just have the constant term 5 to multiply by every term in the second trinomial. So 5 times x squared is 5x squared. 5 times negative 2x is negative 10x, and 5 times negative 2 is negative 10. Then I have rearranged all of these, and let's see, how many is that? This should be 9, so I've rearranged all 9 of these terms, and descending order, so they're all the like terms are together. I have the x to the fourth in the front because there's no other x to the fourth. But there's a negative 2x cubed here and a negative 2x cubed there, so I put those side by side. And I have a negative 2x squared, a positive 4x squared, and a positive 5x squared. And so I have ordered those all together here. And then there is a positive 4x and a negative 10x, and I put those here. And of course the negative 10, the constant term, is all by itself at the end. Then when you combine negative 2x cubed and negative 2x cubed, you get negative 4x cubed. And the negative 2 plus 4 plus 5 gives us positive 7, right? 5 plus 4 is 9, minus 2 is 7. So we have a positive 7x squared. And then the positive 4x and the negative 10x gives us negative 6x. And of course the constant term is has no other like terms to add to it, and so this is the polynomial that fits these conditions. Question 5 asks us to use long division to identify the oblique asymptote of this rational function. We know it has an oblique asymptote not just because the question references 1, but because the degree of the numerator, which is 2, is exactly 1 greater than the degree of the denominator, which is 1. So as it says, we will use long division to identify that asymptote, and this is the familiar format for long division that we did in grade school, hopefully. And so we put inside this frame here, we put the dividend, which is the numerator, and outside right here to the left we put the divisor, which is the denominator of this rational function. And then our first step is to divide the leading term of the numerator, the leading term of the dividend, 2x squared, by 4x. So 2x squared divided by 4x reduces to x over 2, since 2 over 4 is the same thing as 1 over 2. And x squared divided by x is just x. So one of the x's cancels multiplicatively here. And then x over 2 is the same thing as 1/2 x. So the 1/2 x goes right here above the linear term of the dividend. Since this is a linear term, this is a linear term, we place this 1/2 x above the 6x. Then we multiply the 1/2 times the 4x and the negative 5. 1/2 times 4x is 2x squared, not surprisingly. And that goes right here below the 2x squared in the dividend. And the 1/2 times negative 5 is negative 5/2 x. Now, we subtract this line, the 2x squared minus 5/2 x, from the dividend, and so 2x squared minus 2x squared is 0. 6x is 12/2 x, and so 12/2 x minus a negative 5/2 x is the same thing as 12/2 x plus 5/2 x, which gives us 17/2 x, or as I've written it here, 17x over 2. Then we bring the negative 15 down, and we divide the 17/2 x, or 17x over 2, as I've written it here, by the first term in the divisor again. So this is 17/2, or 17x over 2, divided by 4x over 1. I wrote this as a fraction. I wrote the 4x as a fraction so that I could then rewrite it more clearly, more recognizably, as the fraction in the numerator, 17x over 2, times the reciprocal of 4x over 1, which is 1 over 4x. The x's cancel multiplicatively here. The 17 times 1 is then 17, and the 2 times 4 is then 8. So 17/8 is what we get. when we divide 17 halves x by 4x. That 17/8 then goes here. That's a constant term, and it goes above the constant term of the dividend. And so that then is our oblique asymptote, 1/2 x plus 17/8. If you carried on and multiplied the 17/8 by 4x to get 17 halves x, and then the 17/8 times the negative 55 to get negative 55 halves, which is what it simplifies to, and then subtract this line from this, you'll get the remainder, and the remainder would be out here, but the remainder, as we saw in class, does not contribute anything to that oblique asymptote. And so once we have determined the constant term of this linear function in the quotient, then that's the conclusion, and that is the oblique asymptote of this rational function.